is the last part of the Chapter 6 video study guide. So for these, we want to rewrite these radical um, equations so that they're in this form where we can clearly see the vertical stretch, we can see the horizontal shift, and we can see the vertical shift. So in general, you want to factor out whatever's in front of x. So in this case, there's a 16 in front of x, and we want to factor that out. So if I divide by 16 on the first term, you just get x. If you take 80 and you divide by 16, you just get 5. So when we factor it out, we can write it this way, and that will allow us to clearly see what the vertical stretch, what the horizontal shift specifically are. The vertical shift isn't going to change, you'll notice. But here, if you look at this plus 80 might make you think it's shifted 80 to the left, but that's not true at all. When you pull out that 16, and I'm going to write it separately this time. Remember, the product of radicals is the same thing as the radical of the product. So square root of 16 is just 4. So we get 4 square root of x plus 5 minus 1. So the original form of this wasn't easy. It wasn't easy to see how this is graphically, but let's look at the graph of these. The red function here is the original way that it's written, and I left off the y equals, but it still knows that if I put the y equals, it'll be the same thing. Now let's turn that, instead of having that, let's have the blue function here graphed. And you'll notice how the blue function and the red function, they are the same thing. So the second way of writing this is it's a lot easier to see that this thing is stretched by a factor of 4. It's shifted left by 5. The fact that it's shifted down by 1 is just as easy in the original, but the vertical stretch and horizontal shift are a lot easier to see. So that is the answer in this form it looks a lot like vertex form for parabolas, but we don't call it vertex form, but it has that same kind of that same basic layout. But this is sort of a parabola, kind of. It's the top half of a sideways parabola, which is what a radical function is. So for number 30, we're going to do the exact same thing. We want to get it into that form where we don't have anything in front of x inside the radical because it kind of fogs up what's really going. So we're going to, this time, factor out whatever's in front of the x. In this case, it's a 9. So when I divide by 9, I'll show my work here. When I divide by 9, if you divide the 9x by 9, you just get an x. If you divide the 3 over 9, like if you divide 3 by 9, you get 1/3 when you reduce that. And so I'm going to rewrite this as square root of 9 times square root of x plus 1/3. And so this is 3 times square root of x plus 1/3. So what this should look like is a radical function, but it's taller. It's stretched by a factor of 3 this time, and it's shifted to the left by less than 1 unit, 1/3 of a unit. And we'll get some practice in actually graphing these functions in the next few examples. But in general, this is stretched by a factor of 3, and it's shifted left by 1/3 is what you should understand. For number 31, we're going to practice graphing these. Now, here's what we should know. Before I do anything, I'm going to graph the function y equals square root of x. Now, remember, this is called the parent function. This is just the basic square root of x function. We know that the square root of 0 is 0. The square root of 1 is 1. The square root of 2 is nothing easy to calculate. The square root of 4 is 2. The square root of 9 is 3. So this has this kind of sideways parabola curve. And if we understand that that's what a square root function looks like, well, here's what I can expect here. This function should be twice as tall. So it would, double of 0 is 0. And so I'm going to actually graph these one piece at a time. Let me just graph y equals 2 times square root of x. Instead of the square root of 0 being 0, well, you double 0, you still get 0. If you double 1, you get 2. The square root of 4 is 2, but if you double that, you get 4. The square root of 9 is 3. If you double that, you get 6. Now, this is not the function that I want. This is just that stretched function. What I really want is I want 2 times the square root of x, but then shift it up by 3. So I'm going to take each of these points and move them up by 3. So I get that point right here. I'm going to move this up by 3. You get that point right here. I'm going to take this, move it up by 3. You get that point. And this last one, move it up by 3. So the function that I'm trying to graph is going to be this green curve right there. And I can move those little things right there. So this is the graph of that function. Now, understanding the domain and range, let's look at just the domain of the regular square root function. You can't take the square root of negative numbers and get a real result. So we know that the domain of this is only positive numbers. So you could say from 0 to infinity if you want to use interval notation. Or you could say we can only take the square root of numbers that are bigger than 0, or exactly 0 works too. That is the domain of the. So you can write it either way. Now, the range is a little harder to tell unless you're familiar with the graph, but you're going to be asked to graph these. So you should be able to see the range from there. Well, let's look at the range of just the red function. So the red parent function, just square root of x, we don't seem to be hitting any negative values, but we do seem to be hitting all kinds of positive values. And even though the positive values on this graph stop at about, like 3 or 4, they're going to keep going. If you do square root of 100, you're going to get 10. If you do square root of a million, the square root of a million is 1,000. So we can keep going up as far as we want, but since this is the principal square root function, you're never going to get a negative value. The only way you could get a negative is if they reflected it across the x-axis. So the range of your parent function is also going to be 0 to infinity. Now, if you understand that, okay, we can write it that way. We can write the range is all y values greater than or equal to 0. Either one is cool. This is interval notation. This is inequality notation. You could write out in words too. You could write for the domain, you could write all positive numbers. And then the range here is all positive numbers too. But let's look at the green function. All right, the domain didn't change because you still have square root of x and you still can't square root negatives. But let's look at how the range changed. We shifted it up by 3. We shifted it up by 3. Now look at the graph. The y values start not at 0 like the original red function did. They start at 3 and they keep going up from there. In the green function, we never hit y values of 2. We never hit any y values of 1, and we certainly don't hit any negative values. So the range of this function is going to be, instead of all numbers 0 to infinity, it's going to be 3 to infinity. And you can state that as inequality, y is greater than or equal to 3 if you prefer, or all numbers 3 or higher if you want to write it out just in plain English. The domain in this case isn't going to change. It's still from 0 to infinity. And remember, even if you don't know, even if you don't feel like memorizing the domain and range of the original square root function, even though it really helps if you just understand that you're shifting it, left, right, up, and down, you can just look at the graph. The x values, we don't seem to be using x values that are negative, and we don't end up using y values that are less than 3. So you can just tell by looking at the graph. We'll do some more examples. So for number 32, even though it's not a perfect square root here, I still don't love the fact that there's a number in front of x right there. So I'm going to actually factor that out. So I'm going to rewrite this with that 2 factor. So if you divide the 2 out, if you pull it out or factor it out or reverse distribute it, however you want to say that, but this we basically say factor it out, you get x plus 3 over 2 inside parentheses there. I'm going to go ahead and actually pull the 2 all the way out. So we get negative, and the thing is, with the square root of 2, that actually doesn't simplify to anything. So I'm just going to leave that as like the vertical stretch. And then we have x plus 3 halves inside the radical still. So For the domain, and we just want to basically graph this. We want to roughly sketch this, and then we want to look at what the domain and range of the function is. Now, once that 2 is out of there, I can more easily see what my domain is. Because for my domain here, I know that, again, I can't put negative values into x usually. But here it's like we're adding 3/2. So actually, the lowest x value you can put is whatever makes you have a 0 in the radical. So square root of 0 is legal. So if you just remember that whatever is inside your radical, since that can be 0, you can find the domain without doing this, pulling the 2 out if that's awkward for you. You can just say, oh, well, I know that x plus 3/2 is equal to 0. If like that's the minimum value, it has to be bigger than or equal to 0, because you can take the square root of 0 and you can take the square root of positive numbers. So if you solve for this and you get all numbers that are bigger than or equal to negative 3/2, if you subtract by 3/2 are going to give me good results there. So my domain is going to be all numbers that are bigger than or equal to negative 3/2. That's the inequality notation. Or you could write negative 3/2 to infinity. You could write it in integral notation that way. So either way that works. Now, if you want to get the range, again, it helps to graph this thing. If you have trouble picturing the graph, um, feel free to use your graphing calculator to give you an idea. Let's just put the original function into there. So I'm going to put the negative square root of 2x plus 3, and I'm going to just graph that in the standard window. And I know that normally I wouldn't have a range of negatives, but what makes you have a negative range is the fact that it's reflected across the x-axis. So just look at the y values you think you hit. Normally it would be 0 to infinity, but I'm just going to use the trace button to kind of help you see it. So the y values, we can go as negative as you want. If I just keep going to the right, the negatives are just going to obviously get bigger. But what's the number that's going to be the starting point here? Well, since we normally can't, when we principal square root something, it outputs a positive, but this negative makes it output a negative instead. So instead of your range being 0 to infinity, it's actually 0 to negative infinity. So instead of it being all numbers bigger than 0, the range in this case is all numbers less than 0. And look at when as far left as it allows you to go. So remember how we said you can do it algebraically and see that, okay, just set whatever's inside the radical equal to 0. That tells you your domain. So negative 3/2. If you have trouble doing it algebraically, you can get at least a good guess. Notice how I can go as far left as negative 1.4 and it still returns the y value. Let me go left again. Oh, when I go to negative 1.7, it basically says, no, I can't do that. So negative 1.48, well, negative 1.48 is awfully close to negative 1.5, and that's what negative 3/2 is. So if you just roughly sketch this right here, it's just going to look like, and I'm just going to sketch it really poorly. But if you want to get it more accurate, you can just, you can plot a few more points. But the idea is that it's going to have that shape that's a radical, but it's going to be upside down. I'm going to at least get my y-intercept. That's an easy thing to get. If you plug in a 0 in place of here, you can get your y-intercept. So when you plug in a 0, you get square root of 3. So negative square root of 3. And even if I don't know what negative square root of 3 is, I can use this to find my value right here. Plug in 0. So that's about negative 1.7. So plot that point right there. And I can get as many other points as I want, not just from my graph. So you can get points using the trace key. So I'll move the trace key to about 9, and that maps to a value of about negative 4. So if I go to 9, about negative 4, so I just kind of sketch the curve, And it's that kind of sideways parabola shape, and I know it should be upside down. So the domain is all numbers bigger than negative 3/2, or you can even write it as a decimal. You can do all numbers bigger than negative 1.5. That's fine as well. And then the range instead of all positive numbers like the previous example, your range is all numbers that you could start at 0, but you go to negative infinity. But we don't like to write intervals this way, where you put the biggest number then the smallest number. The better way to write that is negative infinity to 0 if you want to write it in interval notation, or you could just say all y values less than or equal to 0 is just sort of a cleaner way to write it. Or you could write it in words too. But the most important thing, domain, remember that if you just set the thing underneath the radical, so if you like avoid factoring out the square root of 2 here. A better way to do it, if you just care about the domain and you can use your graphing calculator to help you see the graph, or you can like use a table of values. If you just know that we are not allowed to put negatives under a radical, and you set this to be greater than or equal to 0, when you solve for x here, you should get x is greater than or equal to negative 3x. So that's how you find your domain and range from the equation. This will be the last one where we graph, and I'm going to focus on doing this one by hand, and then I'll show you that the graph can help you do it. So doing this only by hand, I know that underneath a radical, you're not supposed to put a negative there. So the thing underneath the radical, remember we call that the radicand, is not supposed to be negative. It's supposed to be not negative. So it could be greater than 0, but 0 does barely make it. So if I want to find your domain by hand, just solve for the x of that integrand. And so we get for our domain all x values that are greater than or equal to 0, or you could say, you could put it in interval notation, everything from 3 to infinity. Either way you put that, you should be able to like recognize both types of answers if it's multiple choice, or and write at least one form of the answer. Okay, so normally a square root function outputs, we know that we can't put negatives in, and we also know that the standard square root function is like sort of a sideways parabola. It only outputs positive numbers. But what does this negative 4 do? Well, a negative 4 takes this function and it shifts it down by 4, so instead of starting at 0, it's going to like start at negative 4. Now, I didn't account for that the 3 shift here because I'm just focusing on the range, but notice that the domain, is affected by the number like the +3, whereas the range is going to be affected by this -4. So domain x values horizontal shift. The horizontal axis is like your domain values. So your vertical shift is going to affect your y values, which is going to be your range values. So we know that the range for this function, instead of the range being from 0 to infinity, since it's shifted down 4, if I take a range of 0 to infinity, if you subtract 4 from 0, you get -4. Now, if you subtract 4 from infinity, you actually still get infinity because you can't really subtract 4 from infinity. But that's maybe a good way to picture it. You can say that the range is everything from -4 to infinity. Just to be consistent, I'm going to write the inequality notation first, interval notation second, and either answer is acceptable. You can say it this way, for domain. You can say it this way for range. You could also say it in words. I just don't do the words because it takes longer to write. But you could say the range is all numbers that are bigger than or equal to -4. Or you could even say -4 or higher, but that's another way to say it. Now, for graphing it, you can do these in any order. If you know your domain and range, it helps you graph it. If you struggle with finding the domain and range algebraically, you can graph it first. Again, either graphing it by hand, you can pick points, you can make a table, you can literally take x values and take y values and just plug in some x values, so like 0, 1, 2, 3, and generate a table by hand, and put dots on here. But if you understand how the domain and range work, we know that, oh, hey, normally I can only put, the lowest number I can put is 0, but because we're adding 3 underneath the radical, you could put like as low as -3. If you do -3 plus 3, you get square root of 0. -2 also works, obviously. you -2, plus 3. You don't get a negative under the radical, you get a positive 1. So, whereas normally I couldn't put a negative inside of x, I can't put a negative under a radical, but since I'm adding 3 to the x, you can actually put a -3 inside the radical. Now, if you put a -3 here, -3 plus 3, that's square root of 0, which is 0. Then we subtract 4. So the x value, -3, outputs a y value of -4. And look at that, where your function starts at the domain value. Oops, I forgot my negative here. Forgive me. -3 comma -4 is sort of like your lowest point on there. And this is not stretched vertically, so I I can confirm this later, but I know that that's going to be a point here. Because in the regular square root function, if this were the y-axis and this were the x-axis, the square root of 0 is 0, the square root of 1 is 1. Even though I'm not there, but if the y and x-axis were here, the square root of 4, which is where 4 would be if this were the x-axis and the y-axis, the square root of 4 is 2, and so on and so forth. The square root of, see, where would 9 be? If this were 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 would be where 6 is because this is shifted 3 units to the left. The square root of 9 is 3, so again, so we'd have this point right here. This would be the 3. Now, I know that's -1, but the reason why that would be the 3 is because we're shifted down by -4. Now, if I lost you there, remember, you have tools. You have a calculator that graphs. Please use your tools. I want you to know how to use this technology. So just graph square root, just like it's saying, exactly what you see. Square root of x plus 3 minus 4. And let's just see if you can get an idea. There you go. There's the graph right there. And if you want to get it a little more precise, this is something that kind of gets in the way, but let me show you something that you may have forgotten you mentioned in class. If you go to format right here, hit second, and then I hit zoom, so it's like second format. You can turn grid on. So I'm going to go down here. I'm going to go to grid. I'm going to hit enter, and I'm going to go back to my graph, and look at that. It has like a little grid. I don't love it. I think maybe the newer versions of the calculators like actually have like that sort of light grid, so it looks better. But you can see a lot better that this point is -3, -4. So you can see the points a little better when you're sketching the graph of that function. Another thing that works even better than that is just go to your table. Again, we have this in y equals. I hit second table. And let me just do this. Let me set my table set to automatically pick values. So it's going to automatically pick values. So I'm going to go back to second table, and let's see. It has values for 0 and 2 and 3, 4, 5. So it has valid y values for all of these, but let's so I could just plot the points right here. I mean, if you're using the grid that's provided here, going beyond 10 would take you off the grid. So if you look at the x value of 10, we're about at -0.4. If we look at the x value of 6, that's a nice one. X value of 6, we're at -1. If we look at the x value, just plot the nice ones. An x value of 1 maps to a y value of -2. And look, it was already there. An x value of, these are nice ones, -2 maps to a y value of -3. An x value of -3 maps to a y value of -4. That was where our domain started. That was where our range started. Notice when we go less than -3, it won't even graph it. That's because any number less than -3 is not in the domain of that function. So whether you use your table, use the graph, whether you do it algebraically, there's so many tools at your disposal to be able to figure out the domain, the range of the function. Let me get those out of the way, but this is basically what your graph looks like. And you could even appeal to this. If you know the general shape of a square root function, this is not new. Shifting, left or right is this number right here. In this case, it's shifting left because plus inside shifts left. This is shifting down by 4. So all those ways you can use to appeal to kind of visualize the graph of a function. All right, we're going to go over some just reasoning questions, some things we're just going to think through. Why does negative 108 not have real sixth roots? Well, let's ask our calculator. Let's say we have no idea why this doesn't have sixth roots. So we take negative 108, and let's just try to sixth root it. So we can go into our calculator. One way to sixth root something is to raise it to the 1/6 power. So you can just raise this to the 1/6. And let's see what our calculator tells us. I have my calculator, and so there's the answer, but look at the answer here. See how it has an I there? So because my calculator is in A plus BI mode, it will give me an output, but it won't give me a real output. Let's set it to real and see what happens. Let me try that again. And go ahead. Oh, it says non-real answer. The answer is not real. Okay, let me try it. Another way you could type it, by the way. I type this 6, I preload the 6, and I go to math, option 5. See how it sixth roots it? Again, I hit math, option 5, and negative 108. This is the same thing as writing it this way, but again, we get non-real answer. And let's see why it's mad. Let's go to. It's mad at the number we put in there. We put a negative in there. Now, you can't square root, fourth root, sixth root, eighth root. You can't do an even root of a negative number. So, but you can do odd roots of a negative number. So, for instance, you can do the cube root of negative 8. That's cool. But you can't do the square root of, say, negative 8 or negative anything. This is not cool. So, evens do not like to do roots of negatives if you have an even index. Okay, for 35, we want to write a relation that itself is not a function, but whose inverse is a function. Okay, now you could really kind of cheat around this. So, do you know any functions that have inverses that are not functions? Well, the most common one is if you take, like, for instance, x squared. Let's take the function x squared. You could also call it y equals x squared. The y and the y, the f of x are pretty interchangeable as like the output there. Well, I know that if I do the inverse of x squared, I get square root of x, but don't forget you also got to do the plus case and the minus case, plus or minus square root of x. Because square root of x by default means principal square root. So if I want to give a function that is not a relation that is not a function, but whose inverse is a function, I could choose this right. And I'm going to adjust the notation a bit. Since I know that this function has this inverse, let me just do this. Let me say, let's call the function g of x. And let's call the function g of x equal to plus or minus square root of x. The inverse of that function is x squared. So if if f is x squared, the inverse of f is plus or minus square root of x. But if you have a function, if the original function is plus or minus square root of x, then its inverse is x squared. But this is an example of something that just because just because the original relation is a function, the inverse doesn't necessarily have to be. And if you wanted other examples, you could have really any even root is not going to have. So like if I did x to the fourth, okay, the inverse function would be plus or minus the fourth root of x. So you could choose plus or minus fourth root of x, plus or minus square root of x, plus or minus sixth root of x, any even root of x, or you could see it as any even power of x, its inverse function will not itself be a function. Finally, number 36. So here's the thing. We're given a relation between t, which is time, and the length of a pendulum. And this is actually something we discovered from physics. This is pretty accurate. There are some, if depending on the weight of the string, it can vary a little bit possibly. But we're asked this: if the pendulum is 10 centimeters long, okay, how long? And when they say how long, they mean how much time is a cycle. When they say cycle, they mean measure it specifically in seconds. So a cycle t in seconds is given by 2/10 times the square root of L meaning the length. Well, we can just plug this in. All we're doing is evaluating the function for this. So we're fed, this function is designed to be fed a length, 10 centimeters. I'm putting the centimeters really small. I really just don't want to getting in the way. And honestly, you evaluate that, meaning you calculate it based on that value 10. So you get it to zero point 0.2 times, you could put the multiplication symbol, but it's not necessary, square root of 10. And so you get about, they said to the nearest tenth, so 0.63, so just zero point 0.6. So about 0.6 seconds. And then let's try it again, evaluate it instead of a string that's 10 centimeters long. Let's do 20 centimeters long. Just scroll up here, hit up twice, hit enter, change that 10 to a 20, and we get that answer there. So calculating it in this direction is really easy because this function is designed to be fed length and spit out time. But the last question is a little different. Okay, so remember our formula is this, our relation, we should say, is given here. But what if instead of giving us length, they give us seconds, they give us time? So let's put a 2 right here, and I'm going to put a tiny s for seconds, but I don't like the unit getting in the way. T is equal to 2/10 times square root of L. Well, we have a problem. This is not as easy to just put into our calculator, okay? So we have to solve for L, but to do that, we got to get L by itself. Well, first things first, let's get rid of this 0.2. You could have squared both sides, but you'd have to square the 0.2 itself, so that's why I recommend dividing the 0.2 out first, and dividing those 2/10. And I'm not going to put this in my calculator. Again, I highly advise don't pick up your calculator until you have everything that you need. Excuse me. So we got 2 over 2/10 is equal to square root of L. Well, how do we get L by itself? We got to get rid of that radical by squaring both sides, but be careful. I want to square both sides. Don't just square the 2, square the entire side of the equation. So now we're ready to put this into our calculator. I'm going to do 2 divided by 2/10. Be very careful. It's important that we use parentheses there. Square that, and that gives us the answer. So that's a length of 100. Now don't just say 100. They say how long in centimeters. So the answer is 100 centimeters. That is it for the study guide. And just a reminder, if you wanted one other way to do that, you can also use alpha y equals if you want to make the fraction look a little better. 2 over 0.2 if that makes you more comfortable. And then when I square it, notice how I'm just hitting this right here and I hit enter. It makes me a little nervous not putting the parentheses, but whenever you do the alpha y equals, it does assume that I'm trying to square both sides. But usually just as a precaution, I'll put the parentheses anyway, like this, because it just makes me more confident that my answer is correct. But that's it. Good luck on your test.